Hey everyone, I just want to use this video to talk a little bit about probability. We're just going to do the basics here, and then maybe learn and or, and call it there. So let's see what we are going to talk about. All right, so the first thing we have to do with probability is talk about terms. The definitions, there's a lot of language that goes with probability, and so we want to know what that is so that we can just start using it right away. There is one thing I will caution you to look out for. In probability and a lot of statistics, everything is called P because P stands for probability, and probability is what we do in stats essentially. There's tons of it, so there's gonna be lots of P's, P value, P hat, P bar, other things. Yeah, so watch out for all the P's, and when you see a letter P representing something, be really careful that you know what it stands for because it could be a variety of things. Okay, that said, let's talk about probability. So first, what probability is the long-term likelihood of something happening. Just because the probability of something is high doesn't mean it necessarily will happen, right? 90% probabilities don't come up 10% of the time, right? So if there's a 90% likelihood of something happening, doesn't mean it will happen. It just means that it will probably happen. And then if it doesn't mean that the person who told you that is wrong. Yeah, so it's the long-term likelihood of things happening. We're going to do what's called classical probability here, where we're going to be like rolling dice and picking cards and things like that, because it's a good introduction. So rolling a 1 on a 6-sided die, the probability of that is 1/6, assuming the die is fair, which they generally are. That doesn't mean that you can't roll 10 ones in a row. You totally can. It's not very likely that you will, but you could. And so what probability means is it's the long-term average, right? If I rolled not 10 but a billion dice, they wouldn't all come up once. They could, but the probability is so low that it would very likely not happen. And so it's the long-term likelihood. Like if you did something an infinite number of times, what proportion of them would be? What proportion of the outcomes would be this outcome that we're interested in? Generally, it's pretty easy to calculate probability. Mostly, like for most of what we're doing here, it's going to be just how many outcomes are you interested in divided by how many outcomes are there. That'll usually give you what you want here. A couple things to note about probability. It's always between 0 and 1, or you can express it in percentages if you want, 0% and 100%. Can't have negative probability. That makes no sense at all. Can't have probability greater than 100%. That makes no sense either. It cannot be 110% likely that something happens. If it is certain to happen, it is 100% likely. So more doesn't make any sense. Secondly, the notation looks like this. Your basic probability notation looks a lot like function notation from algebra, but it's P and then in parentheses, whatever thing you're looking for. So capital P and then in parentheses, whatever event you are trying to describe. All right. And I used a couple terms there already, outcome and event, that we're going to talk about now. Probability experiment is just doing something like flipping a coin or rolling a die. Or you can define other things as probability experiments. Like, for instance, you can see down here in example 1, I have flip 3 coins. I'm thinking of that as my experiment. I'm just going to flip 3 coins. And these guys all sort of go together. Trial, outcome, event, and sample space. So trial is running your experiment once, or it's one iteration of your experiment. So if your experiment is to flip a coin, it is flipping a coin once. That's the trial. Outcome is whatever the result of that was. Whatever the heads, for instance, would be one outcome. Or down here, for instance, when my trials are all flipping 3 coins, right? You flip a coin 3 times. That's one trial. Then an outcome might be something like tails, tails, tails. An event is a collection of outcomes. So it's some group of outcomes that you are defining. So for instance, I could say that an event would be, so if I flip 3 coins, an event would be something like, oh, I get at least 1 head, right? So there are several outcomes with at least 1 head in. Specifically, there are 7, which we'll see in a second. And those outcomes together form an event. The event is some collection of outcomes, and that you can see whether or not the actual outcome you get falls into. And sample space is the list of all the possible outcomes. That's it. Not all the events, all the possible outcomes is the sample space. Probability distribution is very similar to these things, but it is not just a sample space. It's the sample space along with the probability of each of the outcomes. This often comes to us in the form of a table or a graph, because in some probability experiments, there might be an infinite number of outcomes. Like, for instance, how much water did I put in this water bottle, or how much water does this water bottle contain, right? Where it could be anything between 0 and however much water the bottle can contain. Well, there's an infinite number of different amounts of water in there, right? And so your probability distribution has to have it, or your sample space has an infinite number of outcomes, and your probability distribution has to show the probability of each of them. So something like that usually gets a graph, or possibly a name of a distribution that we'll talk about later. But sometimes there are infinite outcomes. Those are not the ones we're going to deal with right now. We're just going to deal with the simple finite ones, basically. And then the last one, sort of unrelated to the others, a complement. So if A is an event, so this is some collection of outcomes, then all the outcomes that are not in A, but are possible, of course, is called the complement effect. So for instance, if I'm looking, well, you know what, let me talk about this in just a second down here. I'll bring up complement in just a sec. Just a quick note, when you're doing probability, sometimes usually even, it's better to leave your fractions unreduced, which I know is going to anger a lot of algebra teachers, but still, it's generally better to leave your fractions unreduced. We'll talk about why a little bit later, especially when we get to example 2 near the end of this video. We'll see why. And then let me talk about complements here. So I first want to show you how to draw a tree diagram. It takes a little bit of doing. Tree diagrams are pretty big too, so you don't want to usually do them for something with too many outcomes. But here's my experiment. We're going to flip 3 coins. Each one's going to be heads or tails. We're just going to assume 50% probability of either one. And so one outcome is something like this, HTH, right? So I flipped 3 coins and I got heads and tails and heads. And so an event would be any collection of these different events. And it turns out there are 8 of them. Excuse me. An event would be a collection of different outcomes. It turns out there's 8 different outcomes that you could get. And you don't have to have like a description of at least one H. It's okay to just say, yeah, my event is this outcome and this outcome and this one. Nothing else, that's an event. Just those 3 outcomes together. You can just like list them out, and that's a legitimate event. All right, so let me show you what a tree diagram is. I always have people who haven't seen these before, which the first time I taught this class, I just assumed everyone knew what a tree diagram was, but a bunch of people hadn't seen it. So in every class since, I have not been surprised when people didn't know them. So here's what I'm going to do for a tree diagram. Tree diagrams are kind of, they look like an upside down tree, actually, with the leaves at the bottom and the root at the top. Here's how it works. I'm flipping 3 coins here, and that means that at each flip, I have a choice. Not choice exactly, but there's 2 different outcomes, right? I can get a head or a tail. And so what I'm going to do is I'm going to draw little lines signifying those, right? So this is my heads branch and my tails branch. And I'm thinking of this this first node here as like each node is going to be a flip, basically. And then my second one, I could get a heads or tails, or a heads or tails. And notice that each of these branches assumes that one of the things has happened, right? So down this branch here, I've already flipped 1 heads, and then once I do that, I can get a heads or a tails. Or I've already flipped 1 tails, and once I do that, I can get a heads or a tails. And that idea of doing one first and then what can happen next turns out to be pretty important in probability. It's called conditional probability. That's not going to be in this video. I'll put that in the next one, I think. And then I'm flipping 3 coins, and I've only got 2 flips on here, so of course I can do a 3rd flip. Oop, I didn't leave myself enough room. That's the classic blunder in making a tree diagram. They get big really fast, so you have to leave yourself a ton of room. So yeah, give yourself enough room to let your tree diagram spread out. Now the way you read this is, for instance, this You start at the root, which was the first flip, and you go down a path. And so that path is heads, heads, heads. And you can do all the 7 other paths too, right? Heads, heads, tails, heads, etc. Right? And so that's a tree diagram. One thing that we'll see a little bit later is that you can put the probability of each of these things on the branch, on the branch representing that particular outcome. So you write the probability of that outcome. And then if you want to know what the probability of one of the outcomes at the event at the end is, you just multiply. You just multiply down the tree, which is really helpful, actually. That's one of the reasons this is a useful visualization tool. Do notice that if you have too many different outcomes, your tree diagram is probably too large to be useful. And we'll see some other things that you might want to do, like maybe a Venn diagram or a table or something like that. But I like this as a visualization tool. I think it's really nice. All right, so this is how you make a tree diagram. Let me go ahead and go back to go back to the notes here. Oh, and one thing I should point out, if I went left to right along the bottom of the tree, I would get these 8 outcomes in order. And by the way you can tell how many there are going to be is at each node, you recognize how many choices you've got. Where'd it go? That is. So I have 2 choices at the first layer. I have 2 choices, right? There's 2 different outcomes I can get. Now at the second layer, I have 2 different outcomes for each of these nodes. In the third layer, it's also 2 different outcomes. And so I would have 2 times 2 times 2 is 8 outcomes, which is how many you have. Your tree diagrams don't always have to have just 2 or even the same number in each level. They do have to have the same at any given level. That level has to have the same number of choices, but I guess not. I guess not. If you're getting really fancy tree diagrams, that's not even true. Let me show you an example. For instance, like let's say I have Bob owns like 2 pairs of shoes, 2 pairs shoes, 3 pants, 3 pairs pants, and 4 shirts. Right, and then I want to make a tree diagram for this. I'm not going to make the whole thing; it'd be quite large. It'd actually be 24 outcomes along the bottom of the screen. But I'll make enough of it so you can see where I'm going with this. Right, so he has 2 pairs of shoes, so he's got 2 choices: shoe 1, shoe 2. My handwriting, oh my God, it's worse than usual. And then once he's chosen those, then he has 3 pairs of pants. So he's got pant 1, pant 2, pant 3, P1. P2, P3, right? And you'd have the same thing over here. And then for each of these pants outcomes, he has 4 shirt outcomes. Shirt, 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 shirt. Shirt 1, shirt 2, shirt 3, shirt 4. Right, and you can imagine that I could do the same thing. Put 4 shirts off of the end of each of these pants outcomes and off each of these pants outcomes. And so you can see why the number of outcomes is the number of choices at each layer, right? So there's 2 different outcomes between the 2 pairs of shoes that Bob owns. Bob probably gets more clothes, but regardless of that, he only owns 2 pairs of shoes right now. And then so that leads to 2 different sets of 3, right? So 2 times 3 outcomes at the second layer. And each of those 6 outcomes leads to 4 different choices for shirts, right? So he's got 2 times 3 times 4 choices for outfits that he can wear, right? And so you can draw a tree diagram of that. You just count the number of choices at each level, multiply them all together, and that's how many outcomes there are. So if Bob was picking one of these things at random, one of these outfits at random, he would have a 1 out of 24 chance of getting it because we have 24 equally likely outfits, right? And so picking one of them at random would give him a 1 out of 24 chance. So that's the basics of tree diagrams. Let me go back to the notes. Okay, so I want A to be the event exactly 1 tails. So in other words, when we're flipping 3 coins, what I'm going to do is figure out what the probability of this is, right? So I'm going to list all the outcomes in A, and then I'm going to circle them on my tree diagram. I'm actually not going to remake the whole tree diagram. I'm just going to list them all out. So let me go back to the whiteboard here, clear this off, and list out all the outcomes, right? So we've got heads, 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 tails, heads, tails, heads, heads, tails, 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 heads, heads, tails, heads, tails, 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 heads, tails, tails, tails. You may be able to tell that I have made this diagram. Okay. So I'm going to circle the ones that have exactly one tails, right? So the ones with exactly one tails are this guy here, and where are the other ones? This one here, and this one here. There are 3 of them. So if I were to flip 3 coins, I would have a 3 out of 8 chance of getting one of those guys. There are 8 outcomes, 3 of the ones that I'm interested in. So the way I would want to write this is something like this: probability of exactly one tails, exactly 1t equals 3 out of 8, where this is outcomes we're interested in. And then this guy is total outcomes. Right. So one thing to notice, this particular just counted up method only works if everything's equally likely. If heads and tails were not equally likely, the probability wouldn't be 3 out of 8, but we're not going to worry about that right now. For right now, we're basically just counting stuff. We're just counting stuff and making fractions. We'll talk about what to do when things are not equally likely in a little bit. So there you go. That's the probability of getting exactly 1 tails. You might also do something. You might also want to write that like this: probability of that t equals 1. Right. That's going to be a common format. Statisticians and mathematicians don't like to use words a lot of the time, even when it would be clearer. But this would right here would be a really common way to write this as well. And by the way, when I say they don't like to use words, even when it would be clearer, don't let that make you not use words. Feel free to use words when you're doing these things. Totally fine. You just have to get across the right idea. Whether you do that with words or all symbols, like a lot of statisticians and mathematicians like to do, that's up to you. All right. So, I did that. I listed all the outcomes in A and circled them in my sample space. I could have done it on the tree diagram, but I erased it, of course. I want to find the probability of A, which I did, right? It's 3 out of 8. And then I want to find the probability of A complement. Okay, so remember that A complement is all the things that aren't in A, right? So all of these guys here are in A complement. And these guys. That's A complement. That is a huge prime. That's bigger than I meant to make it. It's really just an apostrophe. There we go. A complement. This is the notation your book uses for complement. Some books also do this, A sub C, or this tilde A. All of those are pretty standard notations for complement. I'm just going to go ahead and use this one, even though it leads to some awkward problems sometimes. But I'll just use the one that your book uses so that it's more readable. So A complement. Oh, I should have mentioned that this. I forgot I gave this thing a name. So probability that t equals 1 is another way to write this. I forgot I had called it A, so that's actually how you'd usually write it, is B of A. Right? This really means the probability that the outcome that you get ends up or is one of the outcomes in A. That's how you would read this, probability of A. So the thing that I'm looking for here for the probability of A complement, of course, there's 5 things that are not in A, right? There were 3 in A and 8 total things. There's 5 that aren't. Is 5 out of 8. So I would say that the probability of A complement was that this was A now. lime green. So I would say that the probability of a complement is 5 out of 8. Pretty straightforward, really. We're still just counting stuff here. All right, let's go back to the notes. And then the thing you want to notice about the probability of A and the probability of A complement is that they add up to 1. It's always true. A and A complement do what's called partitioning, in this case, the sample space, where all of the outcomes are either in one or the other and there's no overlap, right? So if you are in A, you're in one of the red out, or it's one of the red outcomes. And if you're in A complement, it's one of the green outcomes. And it's very specifically all of the rest of the outcomes other than the ones that are in A complement, right? So they cover everything, right? If it's either an A or it's an A complement and there's no other choices. So what that means is the total has to be, in this case, 8 out of 8, right? So they have to add up to 1. If I add the probability of A complement to the probability of A, I always get 1. And that's always true. That turns out to be really useful. I know it seems, trivial and obvious, but it does turn out to be super helpful. So we're going to use that a little bit later. I don't remember if we're doing that in this video or the next one. We'll see. Sorry, I forget exactly where this goes to. Okay, do you think that relationship will hold true in general? Absolutely, yes. Always true. Probability of A plus probability of A complement equals 1. All right, so this is going to be a bit of a complicated example. I know it looks really short. It's not. So strap in for this one. So I'm going to have 3 different events. So firstly, my experiment is rolling 2 dice, and we're going to record their values. One of the outcomes would be like 5-1, where the first die is a 5 and the second one's a 1. And we're going to write down the sample space. That is a little awkward, actually. I'm going to show you a nice way to do it in a sec. Yeah. Oh, here's a description of the way, which I have done. I'm not going to make you sit through me doing the whole thing, though. All right, so A is going to be the event that the first roll is 2 or less, B is the event that the second roll is even, and C is the event that the total of the dice is at least 10. And we're going to find the probability of all those things. So first thing we need to do is write down the sample space. So I've already done that, but let me show you how that would go. I'm going to go ahead and get rid of this. All right, so what I'm talking about here is something as a chart that looks something like this. I have roll 1, 1, 2, 3, 4, 5, 6. This is roll 1. Oh, shoot. Sorry, I need to clear all this stuff. I wrote it too high. Now I can't write above it. Roll 1. 1, 2, 3, 4, 5, 6. Roll 2. 1, 2, 3. That's not, I didn't do a good job there. Let's try that again. 1, 2, 3, 4, 5, 6. Now, as you can see that we have 6 options for roll 1 and 6 options for roll 2. So what we learned about tree diagrams before would tell us that there are 36 different outcomes, and there are, right? You can see, I'm gonna fill in this whole table here. I'm not actually, I've got it all typed out to use, but you could fill in this whole table here, and I've done this on the board a million times, where you get something like this. 1, what's this, 2, 1, 3, 1, etc., 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 right? All the way down to 6, 6 over here, 6, 6. Right, so we have 36 different outcomes here, and it's really helpful to get some kind of table going, right? If you just tried to write all these out, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 1, 2, 1, 2, 2, 2, 3, 2, 4, 2, 5. Like, it's messy and long, right? You don't want to write them all out in a string. Using good visualization tools like getting them all on a chart is really helpful. Really, really helpful for picking out which things you're interested in. So let me switch over here. I believe I've got should have this up somewhere. I think yeah, there we go. Here, I did this, right? So I've got my chart here. Right. So I switched the roll 1 and roll 2 from my whiteboard. Sorry. So roll 1's down the side here and roll 2 is across the top. So this means I got 1 on the first roll and a 1 on the second roll. 1 on the first roll, 2 on the second roll, et cetera, et cetera, et cetera. So event A, I will need to notate Wait, did I switch this? Yes, okay, good. So let's go back here for a second. A is the first roll is 2 or less. B is the second roll is even. And C is the total of the dice is at least 10. Okay. Can I blow this up a little bit? Good. Okay. So what we're going to have here is going to look like this. We said that A is that the first roll is 2 or less. So that is going to be, I'm going to do that in red. So first roll, that's roll 1 is 2 or less. So that's 1 or 2 on the first roll. So that is this stuff here, right? So here's A. B was that the first roll, or excuse me, that the second roll was even. So let's do that guy in orange, I guess. Second roll even is, the second roll is 2, 4, or 6. So this one, oh, that's not that different from red. Maybe I'm going to use a different color. I don't like that color choice. That was unwise. Do green. There we go. That's nice and different. And that's event B. And then event C is that the total is 10 or more. So let's do that in pink. No, let's do black. That'll look nice and different. So C is that the total is 10 or more. That's these guys. You might have to think about where you would find those at first, but it's in the lower right corner where all the big numbers are, right? So that's C. And so we can see that some of these things overlap, right? Some of the outcomes in event A are also in event B, and some of the outcomes in event B are also in C, etc. So what I want to find is the probability of A. So the first question, oh, by the way, if I switch my share back, it's going to delete my annotations, so I'm going to leave them there and just tell you what the first question was. Part A of this question was find the probability of A, B, and C, right? So I can find, let's do this, I guess, in black. Sure. So probability of A equals. All right, well, A, there are 12 outcomes in A out of the 36 total outcomes. So it's 1/3. I'm going to write it as 12 out of 36. So this is what I meant by, it's often better to leave your fractions unreduced. So I could certainly turn this into 1/3, and that would not be wrong at all. Totally fine to write that as 1/3. However, if I leave it as 12 out of 36, not only does it tell me that the probability is 1/3, it also tells me that I had 12 outcomes that I was interested in out of 36 total outcomes, right? Which that information gets deleted if you turn it into 1/3. So I'm going to leave it like this, 12 out of 36. And do the other ones, probability of B. So there are, I've got 3 rows or 3 columns of 6 for B, right? So that's got to be 18 out of 36 then. And probability of C is 6 out of 36. Okay, I'm gonna flip back here. Sorry, I'm not switching the screen share back. So the second question is to find probability of A or B, A or C, and B or C. And so let's oops, that's not the right thing. Here's the right one. Oop, what the heck? Why won't it go back? I don't know. Oh, because I don't have the mouse selected, I have the pen selected. Okay. So the second part of this question is to find probability of A or B, and A or C, and B or C. I think I might do part C first. Yeah, I'm going to find probability of A and B, probability of A and C, probability of B and C. So the first thing to note is what the word "and" means in the context of probability. And means falls into both categories. So something like probability of, oh, sorry, I have to go back to annotate. So if I want to find the probability of A and B, what that's really asking is how many of the outcomes fall into both event A and event B? And there are 6 of them. You can see they're these guys right here. 1, 2, 2, 2, 1, 4, 2, 4, and 1, 6, 2, 6, right? All of the ones that had a first roll of 2 or less and a second roll that was even, right? That's what the and means. So this is 6 out of 36. And similarly for the others, probability, I guess I'm running out of room a little bit here. Probability of A and C. This one's kind of interesting because there aren't any events that fall into both category or both event A and event C, right? If you get a 2 or less on your first roll, you cannot have a total that is bigger than 10 or that is at least 10. The maximum total you could have would be 8. So because this is impossible, 0. Probability of A and C is 0. You can write it as 0 out of 36 if you want. I'm just going to leave it as 0. And when you see a probability of 0, that means that something is impossible, basically. So there's a term for that we're going to get to in just a second called mutually exclusive, where I would say that probability A or that event A and event C are mutually exclusive because you can't be in both at the same time, right? There's no outcomes that are in both. And they're mutually exclusive things have probability 0. If I want to find the probability of B and C, again, I'm looking for how many events fall into both B and C. So there are these guys, 6, 4, 4, 6, 5, 6, and 6, 6. So 4 events out of the 36 fall into those. So this is 4 out of 36. There you go. That's how you calculate and. You're just looking for where things overlap and how many events fall into both categories, essentially. And then the last one I want to do is the probability of B or C, or A or B, A or C, and B or C, because we're going to use those in a little bit. I'm running out of room here, and I don't know how to get another page without deleting everything. So I will just say this. If you're watching this video right now, write down these numbers. I remember them, so I'm just going to use them. And so I'm going to expect that you know all these. So quickly take a screen or quickly pause the video and write them down if you haven't yet, because I'm going to delete all this and then we're going to go on a little bit more. All right. Delete all this. And then delete all of this. Oh, that's going to get rid of the B and the C. Can I get just, yeah, there we go. That, and then swoop there. Okay, so then the way I'm going to find the probability of B or C, A or B, A or C, and B or C, is that I'm going to count up all of the outcomes that are in either of them. So for instance, is it not in write mode? It's not. So for instance, oh, come on. Come on. Sorry, Zoom is being a problem here. There we go. So if I want the probability of A or B, what I'm looking for is all of the events that are in, all of the outcomes that are in either event A or event B, or both. It can be both. This OR is called inclusive OR, which means it includes the ones that are in both. There is another version called exclusive OR, where if it's in both of them, then it doesn't count, but we're not doing that. In general, in statistics, if you hear OR, it means inclusive OR. So it can be in both of them. Now, the thing I do want to point out here is you don't want to double count anything. That actually turns out to be a big deal. I just want to count how many outcomes either fall into event A or event B, right? So it's all the ones circled in red and all the ones circled in green. And these ones that are both in red and green still only get counted once each. So I've got 6, 12, 16, 20, 24. right? So the probability of A or B is 24 out of 36. Now, it's going to be very tempting when you look at the original probabilities to say, oh, if I want the probability of A or B, I just add up probability of A and the probability of B and add those together. But you can see that that doesn't work, right? The probability of A or B is not just the sum of the two probabilities, because if you just add them together, you're double counting the overlap, right? If I did probability of A and get 12 out of 36 and probability of B and get 18 out of 36 and add those together, I've counted this one in A and also again in B. So I've double counted it, and the same is true for the other 6 here. So we'll use a formula in just a little bit to calculate these, but just be aware that you don't want to double count. And actually, when the probabilities get complicated, it can actually be fairly hard to figure out if you're double counting or not. But for right now, it's pretty easy. It's all in a chart, right? The chart's a nice visual representation, makes it easy to count stuff. I'm going to do A or C, and you can see the probability of A or C is, well, there's 12 events in A and 6 that are in C, and there's no overlap. So there's no danger of double counting here. It's these 12 and these 6 is 18 out of 36. 18 out of 36. And then the probability of B or C, you can count them up and see that there's going to be, what is that, 18 plus 2 more that weren't already in B, so 20 out of 36. And there you go. That's how you find the OR probability. Now, let me show you the formula for calculating OR using AND. So actually, I believe that's coming a little later. Yeah, let me go ahead and just show it to you right now. I might as well, since we've got a nice visual representation up on the screen here. So I'm just going to do A and B here, so or A or B. So the probability of A or B is probability of A plus probability of B. And you might be saying to yourself, didn't you just say you can't do that? Yes, because there's a little bit more to it. I'm going to go ahead and erase this guy. Such a pain about getting the pencil back. Minus probability of A and B. And so here's the idea. If I want to find the probability of A or B, well, probability of A covers all the stuff in A, and probability of B covers all the stuff in B, and that's great. However, I have counted all of the stuff in the overlap twice each, once in A and once in B. And so I want to subtract off one of those countings, which is what this is, right? So if I do probability of A, 12 out of 36, plus the probability of B is 18 out of 36, minus the probability of the overlap, these 6 things where it overlaps, if you remember from the last screen, probability of A and B was 6 out of 36. I get, in this case, 12 plus 18 minus 6, which is 24, right? That's this number right here. So I'll return to that. We'll explain it with a Venn diagram in roughly the same way, to be honest, in a little bit. Excuse me, not in a little bit in this video, but in the next video. But that's the formula we're going to be using, and yeah, you'll see that a little bit later. So let me pop back to the notes real quick. It's going to delete everything here. So if you want to see this, make sure that you come back here. What am I doing here? Where'd my notes go? All right. So all that got deleted. Yeah, so that was the last thing I wanted to say about kind of the simple versions of probability. So what the terms are, and then what and or mean, and how to calculate them. And I guess mutually exclusive falls into here too. Mutually exclusive, remember, means two things that can't happen together. So in the example I was just doing, that's event A and event C, right? The things with no overlap. If you get a 2 or less on your first roll, it is impossible to have the total be 10 or more, right? Those two things cannot go together. One prevents the other one from happening, right? That's the way you want to think of mutually exclusive. Two things are mutually exclusive if having one of them happen means that the other one becomes impossible. And that is the last thing that I wanted to say about probability for this video. So I'm going to go ahead and end the video here, and then we're going to talk about conditional probability in the next one, and I'll see you in the next video.